In December 2022, history was made at the National Ignition Facility when scientists achieved what many thought impossible, a fusion reaction that produced more energy than it consumed. After 6 decades of attempts, this breakthrough has transformed fusion from a scientific curiosity into a potential commercial reality. Today, we'll explore this momentous achievement, the global race that has followed, and what it means for humanity's energy future. Let's begin with what happened at the National Ignition Facility in December 2022. Scientists at Lawrence Livermore National Laboratory orchestrated a remarkable experiment using 192 high-powered lasers focused on a hydrogen fuel pellet smaller than a peppercorn. These lasers delivered 2.05 megajoules of energy to the target, creating conditions similar to those found in the core of stars. The result was extraordinary. The reaction generated 3.15 megajoules of energy output, marking the first time in history that a controlled fusion experiment produced more energy than was used to initiate it. This achievement, known as fusion ignition or net energy gain, represents a fundamental turning point in our quest to recreate the power source of the stars. Though the reaction lasted less than a billionth of a second and produced only enough energy to boil a few kettles of water, its significance cannot be overstated. After more than 60 years of research and countless failed attempts, scientists finally demonstrated that the basic physics of fusion energy production works as theorized. What makes the NEF breakthrough particularly fascinating is the method used. Unlike the more common magnetic confinement approach employed in tokamak reactors, the National Ignition Facility uses what's called inertial confinement fusion. In this approach, the fuel isn't held in place by powerful magnetic fields. Instead, it's compressed to extreme densities by the world's most powerful laser system. The engineering precision required for this approach is staggering. All 192 laser beams must strike their target within trillionths of a second of each other. Any misalignment or mistiming would prevent fusion from occurring. The target itself, a carefully engineered fuel pellet containing deuterium and tritium isotopes of hydrogen, must be manufactured to exacting specifications. When the lasers strike this pellet, they create a plasma that implodes, generating tremendous pressure and temperature that forces the hydrogen atoms to overcome their natural repulsion and fuse together, releasing enormous energy in the process. The NEF breakthrough has catalyzed an international race to develop commercially viable fusion energy. China's experimental advanced superconducting tokamak, known as EAST, has made remarkable progress, sustaining a fusion reaction at an astounding 120 million degrees Celsius, that's 8 times hotter than the Sun's core, for a record 1,056 seconds, or more than 17 minutes. Meanwhile, in the United Kingdom, Tokamak Energy has developed revolutionary high-temperature superconducting magnets that operate at just 20 degrees above absolute zero. These magnets potentially solve one of fusion's most persistent engineering challenges, creating strong enough magnetic fields to contain the plasma without consuming excessive energy. South Korea's K-Star facility has also made significant advances in plasma containment, while Japan recently began operations of its JT-60SAR tokamak after a decade of construction. Even smaller nations like Switzerland are contributing through companies like Swiss Plasma Center, which is developing compact fusion technologies that could potentially be deployed in urban environments. This diversity of approaches and international competition is driving innovation at an unprecedented pace. Perhaps the most dramatic shift in fusion development has been the surge in private investment. In the past 18 months alone, fusion startups have attracted over $5 billion in private funding, more than the previous decade combined. This marks a significant departure from fusion's historical development, which was primarily funded through government research programs. Today, more than 30 private fusion companies are pursuing various technological approaches. Commonwealth Fusion Systems, backed by Bill Gates and other prominent investors, recently broke ground on a demonstration plant in Massachusetts that aims to produce net energy by 2025, potentially years ahead of government-funded projects. Even more remarkably, Helion Energy received a landmark power purchase agreement from Microsoft, which committed to buying electricity from Helion's planned fusion plant beginning in 2028. This represents the first commercial contract for fusion power in history and signals growing confidence that fusion energy is transitioning from scientific curiosity to commercial reality. The diversity of approaches being pursued, from traditional tokamaks to more experimental designs like stellarators, magnetic mirror machines, and Z-pinch devices, increases the probability that someone will solve the fusion puzzle, perhaps in unexpected ways. Despite recent progress, significant obstacles remain before fusion can contribute to the power grid. One of the most daunting engineering challenges involves the extreme conditions inside a fusion reactor. The plasma in a tokamak fusion device reaches temperatures exceeding 150 million degrees Celsius, hotter than the core of the Sun. Yet the superconducting magnets that contain this plasma must be kept near absolute zero, creating one of the steepest temperature gradients in the known universe across just a few meters of material. Developing materials that can withstand these conditions, including constant bombardment by high-energy neutrons, remains a critical challenge. These materials must maintain their structural integrity and properties for years of operation while being subjected to conditions more extreme than those found almost anywhere else in the universe. Engineers are exploring exotic alloys, ceramic composites, and liquid metal solutions, but long-term testing under fusion-relevant conditions is still needed to validate these approaches. Another major hurdle in fusion development is the tritium fuel supply. Deuterium-tritium fusion offers the most promising path to commercial energy, but tritium is extremely rare on Earth, with global supplies limited to approximately 25 kilograms, less than the weight of a small child. This scarcity presents a significant challenge for scaling fusion to commercial levels. Future fusion plants must solve this problem by breeding their own tritium. This would be accomplished by capturing neutrons from the fusion reaction in a lithium blanket surrounding the reactor core. When neutrons strike lithium atoms, they produce tritium, which can then be extracted and used as fuel. While this process has been demonstrated in laboratory settings, it has never been implemented at scale. The challenge is achieving what's called a tritium breeding ratio above 1.0, meaning each fusion reaction must produce enough tritium to sustain future reactions, plus a small surplus to start new reactors. Current designs project breeding ratios slightly above this critical threshold, but practical implementation remains unproven and represents one of the key challenges for commercial fusion. Controlling the hot, turbulent plasma inside a fusion reactor remains one of the most complex challenges in the field. Plasma is not a well-behaved substance, it's prone to instabilities that can rapidly cool the reaction or damage the reactor walls. These instabilities develop in milliseconds and can destroy months of experimental work if not properly managed. Recent experiments at Princeton Plasma Physics Laboratory have shown promise in using artificial intelligence to predict and respond to these plasma behaviors. By employing machine learning algorithms trained on millions of simulations and previous experimental data, researchers can now adjust magnetic fields in real time to maintain plasma stability. These AI systems can make thousands of minute adjustments per second, far faster than human operators, potentially allowing for more stable plasma containment. This marriage of plasma physics and artificial intelligence represents a new frontier in fusion research, one that may ultimately overcome the unpredictable nature of superheated plasma that has challenged researchers for decades. One of fusion's most compelling advantages is its fuel source. Unlike current energy technologies that rely on finite resources, the primary fuel for fusion, deuterium, can be extracted from ordinary seawater, making it virtually limitless. A single gallon of seawater contains enough fusion fuel potential to equal the energy in 300 gallons of gasoline. To put this in perspective, the oceans contain enough deuterium to meet humanity's current energy needs for billions of years. The other component, tritium, would be bred within the reactor itself from lithium, which is abundant in the Earth's crust and increasingly recoverable from seawater as well. This abundance means fusion could offer energy security to nations regardless of their natural resource endowments. Unlike fossil fuels, which are concentrated in specific geographic regions, the oceans provide democratic access to fusion fuel. Furthermore, fusion produces no greenhouse gases during operation and generates no long-lived radioactive waste. The activated materials in the reactor structure would require careful handling, but would become safe for recycling within 100 years, a stark contrast to the thousands of years required for some fission waste products. Successful fusion development would have profound geopolitical ramifications. Nations that master fusion technology could achieve energy independence while dramatically reducing carbon emissions. This explains why countries like China, which currently opens 2 new coal power plants weekly to meet its growing energy demands, have doubled their fusion research budget in the past 5 years. The European Union has maintained the largest fusion research program through its ITER project in southern France, though recent budget constraints have slowed construction. The United States, after years of relatively modest investment, has recently increased funding for both public and private fusion initiatives. This international competition reflects the high stakes involved. The first nation to develop commercial fusion would gain enormous economic and environmental advantages. They could potentially license the technology, export fusion plants, and reduce their vulnerability to energy market fluctuations. Beyond national interests, fusion could transform global energy politics by reducing dependence on oil and gas-producing regions and minimizing conflicts over energy resources. However, this transition would create new winners and losers in the global economy, potentially disrupting nations heavily dependent on fossil fuel exports. The potential applications of fusion energy extend far beyond just generating electricity. With abundant, carbon-free energy, fusion could enable large-scale desalination to address water scarcity, a growing crisis affecting billions of people worldwide. Fusion plants could power direct air capture of carbon dioxide, potentially allowing us to not just stop adding greenhouse gases to the atmosphere but actually remove what's already there. The high-temperature heat from fusion reactors could also provide the energy needed for industrial processes that are difficult to electrify, such as cement and steel production, which together account for nearly 15% of global carbon emissions. These applications could help address climate challenges beyond the electricity sector, which represents only about 25% of global emissions. Fusion could also revolutionize space exploration by providing compact, powerful energy sources for deep space missions. Some researchers are already exploring designs for fusion-powered spacecraft that could dramatically reduce travel times to Mars and beyond. The abundant energy from fusion might even enable large-scale manufacturing in space, opening new frontiers for human activity beyond Earth. The fusion energy landscape has transformed dramatically in recent years, shifting from a distant scientific curiosity to a technology with clear commercialization pathways. The next decade will likely determine which approaches to fusion prove most viable for commercial deployment. The traditional tokamak design, exemplified by ITER, competes with more innovative approaches from private companies. Some startups are betting on smaller, faster-to-build designs that might reach commercialization sooner, even if they're less efficient than larger plants. Others are pursuing entirely different confinement concepts that could leapfrog conventional approaches. This technological diversity, combined with the urgency of addressing climate change, has created a uniquely fertile environment for fusion development. Regulatory frameworks are struggling to keep pace with these advances. The Nuclear Regulatory Commission in the United States recently initiated a process to develop specific regulations for fusion energy systems, acknowledging that existing rules designed for fission reactors are inappropriate for the fundamentally different fusion process. How these regulations develop will significantly impact the speed of commercial deployment. Too restrictive, and they could unnecessarily delay fusion's benefits; too lenient, and they might fail to address legitimate safety concerns, though fusion's inherent safety advantages make this less problematic than for other energy technologies. The question surrounding fusion is no longer whether it will be achieved, but when and by whom. The combination of scientific breakthroughs, private investment, and international competition has created unprecedented momentum. If successful, fusion energy would represent one of humanity's most outstanding achievements, harnessing the power of the stars to provide clean, safe, and abundant energy for future generations. The race is not just about scientific prestige or commercial profit, but about securing a sustainable energy future for our planet. The fusion breakthrough at NEF validated decades of theoretical work and opened new possibilities, but the journey from scientific demonstration to commercial power plants remains challenging. The engineering hurdles are formidable, from materials that can withstand extreme conditions to tritium, breeding systems that must work reliably for years. Yet the potential rewards are equally enormous. Fusion offers a path to energy production that doesn't contribute to climate change, doesn't produce long-lived radioactive waste, can't experience catastrophic meltdowns, and uses fuel that's available to all nations. This combination of advantages explains why, despite the technical challenges, investment and research continue to accelerate. The fusion breakthrough of December 2022 marked a pivotal moment in humanity's energy journey. For the first time, scientists demonstrated that we can create a reaction producing more energy than we put in, the fundamental requirement for any viable energy source. While the path from this laboratory achievement to commercial power plants remains challenging, the combination of scientific progress, private investment, and international competition has transformed fusion's prospects. The race to harness the power of stars here on Earth has accelerated dramatically, with nations and companies pursuing diverse approaches that increase our chances of success. The engineering challenges remain formidable, from containing plasma temperatures hotter than the sun to breeding tritium fuel, and developing materials that can withstand extreme conditions. Yet the potential rewards are equally enormous: clean, safe, and virtually limitless energy that could transform our relationship with the planet and each other. Fusion represents not just a new energy technology, but a new relationship with energy itself, one of abundance rather than scarcity, of universal access rather than geopolitical advantage, of harmony with our environment rather than damage to it. The next decade will be critical in determining which fusion approaches succeed and how quickly they can be deployed. But one thing is clear: fusion has moved from the realm of scientific curiosity to technological inevitability. The only questions remaining are when it will power our civilization, and which approaches will lead us there first. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated.